Just here, and but we are now looking at the just geometrical defects in this problem. So
good afternoon. My name is Ti6Al4V, and I'm a PhD student at the University of Trento in Italy. Today I will present you some results regarding the effect of the geometrical defects.
sorry, yeah, it's my mistake. So if you are looking, Susan, surprised at your at your program, the title is the same, but the authors are totally wrong.
Oh.
So that's why. So that's why. Please do suggest. So we have 5 authors who are totally different. They have nothing to do. So just with the group of Maksaki from UK. So, yeah. Thank you for your presentation. Yeah, of your team. Yeah.
So the results regarding. So I'm presenting the effects of geometrical defects introduced by the manufacturing process, which in my case is the selective laser melting, on the mechanical properties, and specifically the elastic modulus and the stress concentration at the junctions between the struts. So this has been already introduced by a previous presentation, but the advantage of several materials in the biomedical field is due to the fact that they are porous, so they allow bone integration, and they also avoid the stress shielding phenomenon, which is basically due to the difference in stiffness between an implant and the bone. If we use a fully dense implant, which is much stiffer than the bone, we basically underload the bone nearby the implant, which is then the bone then will resolve, and thus the interface between the implant and the bone is weakened. So additive manufacturing, on the other hand, is in relation to several materials, is a very powerful tool because it allows to produce a wide range of structural morphologies and also rather complex shapes. But this manufacturing process has also some disadvantages. Namely, in the case of selective laser melting, in particular, are a number of defects which are introduced in the structure. We have defects like porosity, which are mainly due to the trapped gas or incomplete melting, surface irregularities, which are basically due to the adhesion of particles on the surface. We have geometrical irregularities, which is the topic of my presentation, which we can show, or we can see here. This is a tomography I will talk about. So we see that there is a clearly visible difference between the designed component and what we actually obtain. And finally, there might be residual stresses also in the structure, which cause difference between the predicted mechanical properties and the measured ones. So in my work, the aim of this work basically is to use the data from computed tomography of a several sample, and which is then analyzed, imported in MATLAB, analyzed, measurements are carried out, and this data is used to build finite element models which include these defects, and the results of these simulations are compared with the experimental results. So the specimen that I studied is a very simple structure. It's a regular cubic structure with circular struts. The material is titanium, aluminum, vanadium, allowing to produce via selective laser melting. And the important aspect is that the weight has been printed. So it has been printed at 45 degrees to the orientation of the natural orientation of the sample specimen. So we have one series of struts which are in the printing plane, while the other 2 are inclined at 45 degrees. This will be important. So to give you an idea of the size, the units are size 1.5 millimeter. And the section is a circular of the strut. So from these are the results, parts of the tomography. The blue points are the surface extracted from the tomography. This is just a let's say even from a qualitative analysis, we immediately see that there are a number of effects. If we compare the CAD, which is the gray, and the obtained structure, you observe that there is a variability in the cross-section of the strats, and there is also an offset. You can see here the red points are the center of the cross-section, while the green line represents the ideal axis of the strat. We see that there is a sort of waviness in the strat. We can have also a stress eccentricity, which is the deviation basically of the cross-section from the designed circular shape. And there is also an offset of the center of the junction. And we can also have missing or interrupted strats due to errors in the printing process. This was a more qualitative analysis. With MATLAB, I carried out also a more quantitative analysis. And the following four parameters were measured. I measured the cross-section equivalent radius, the cross-section eccentricity, and also the cross-section orientation with respect to an XYZ reference axis, which is basically aligned with the cubic structure, and also the offset of the cross-section center with respect to the ideal position. So a statistical analysis has been carried out of this data, which is summarized in this slide. In this graph, I show the normalized deviation of the cross-section radius with respect to the nominal value. You immediately see that all the strats have a positive deviation, which means that they are thicker than what it was designed, but in particular the strats, which are the blue ones, which are the ones found in the printing plane, are considerably thicker than designed, and also the distribution is wider, which means that they are not only thicker but also reproduce with less precision. And while on the left, this graph shows the offset of the center of the cross-section from the ideal position. And we need to see that there is an offset, and again, the strats found in the printing plane have a greater offset from the ideal position. So basically, this is also confirmed in this slide, where the sections has been fitted with an ellipse, and this ellipse are all the ellipse for all the strats are plotted in the same graph to give you an idea of the orientation and their size with respect to the ideal, let's say, nominal, which is this circular line. So we see that the strats parallel to the printing plane are there's a quite high eccentricity, and they are also aligned from 45 degrees, which is exactly the printing direction. So basically, this is the vertical printing direction. We have an ellipse which is as a major axis oriented as the printing direction. So we can, from this observation, we can immediately conclude that in general we have geometrical defects in this kind of structure, and in particular strats which are aligned with zero or even small angles to the printing plane. They have high defectiveness, and this, as we will see in the next slide, affect the mechanical properties. So the data collected from the tomography was used to build finite element models. I prepared beam models. This is just a part. The beam model is of the entire specimen with the same number of unit cells. The strats were matched with beam elements, and each roughly 20 beam elements per strat. And to each section, I was able to, I independently could assign the offset and the radius. So four beam models were built with a different amount of defects. I felt I prepared a beam model which included the variability in the cross-section radius, but the offset was kept at zero. Another beam model had a constant diameter equal to the mean value calculated with the tomography, but the offset was, the values of the offset were taken from the distribution. Another BIM model which combined these two types of defects, and finally a more complex model which also included broken strut, and the position of the junction was not the nominal one but was varied according to the measurement. So the analysis were, important to say, all in linear elastic assumption and small displacement assumption. So all apart from BIM models, also solid models were used. In this case, only the unit cells could be modeled due to the computational power requested to solve this kind of problem. So 80 junctions were selected from the tomography and meshed solid elements, and axial loading was applied. In this case, from the elastic modulus was measured, and also the stress concentration at the junction. So the stress concentration was defined as the maximum for mesostress at the junction divided by the homogeneous nominal stress acting on the unit cell. So to go to the results, here are the results regarding the elastic modulus. We compare the results from the experimental test with the various simulations. So here, for the second column represents the stiffness value, and the nominal stiffness value calculated from the ideal TED 3D model. You see that there is a difference, due to the defect. In fact, if we take the value measured from the solid model taken from the tomography, we see that the value is closer to the experimental value, although there is a big variability due to the fact that I used only a single junction and not the entire specimen. It's a mean of 8 different junctions, obviously due to the variability of the process. There is significantly scattered. Regarding the beam models, I think this is even more interesting in the sense that the beam model, which includes only the cross-section, but the offset is 0. This has the highest stiffness, but as soon as we introduce the strut weightiness, the stiffness drops. This is particularly true for this type of structure, which is stretching dominated. In case maybe of a bending dominated several structure, the results might be slightly different. And finally, by introducing all the defects, including also the missing strut and the nodal displacement, we obtain a stiffness value which is pretty close to the experimental value. So what we learned from this slide again is that the defects have an influence even on a macroscopic property like the elastic modulus. So when we work with this kind of structure, it is important to take into account also the manufacturing process in the design phase, because we design a component without taking into account the possibility of the defects, especially in the case of several materials, we might not match the expected values. Regarding the stress concentration factor, which I also evaluated from the state junction, I compare this value with the stress concentration factor calculated from the CAD model, and in general I observed an average of 20% increase in the stress concentration factor with respect to the nominal. This is a rather expected result, although it is the real junctions are slightly less detrimental than expected from a fatigue test we carried out in previous work, where we calculated the fatigue notch factor, which is defined as the ratio between the fatigue resistance of a bulk, a notch specimen, divided by the fatigue resistance of that kind of specimen, where the fatigue notch factor was pretty high. But this fact, this difference in results might be due to the fact that I analyzed only a few number of junctions, and there might be also detrimental residual stresses in the structure which have not been taken into account, or also small distortions of the specimen in the testing machine, and possible presence of free group alpha case on the surface of the stress, which may weaken make more gripple the structure. So to conclude, I have analyzed the effect of the geometrical effect on the elastic modulus and the stress concentration factor of the cellular structure with the aid of computed tomography and finite element analysis. And overall, I observed that there is a remarkable effect of defects on the mechanical properties. And the lesson learned from this study is that in the design of cellular materials to be produced via additive manufacturing, and in particular selective laser melting, in this case, the manufacturing process must be taken into account even in, let's say, the design phase. So, in practice, this means that maybe it is wise to, if I want a specific property from my lattice, I might have to modify the CAD and to make, in this case, for example, slightly thinner struts in order to get the final result which matches the properties I desire. Okay. So this is what is my current work, let's say, doing after this research is to devise compensation models for cellular materials in order to compensate for the defects, for the systematic defects, the random defects that are more difficult to compensate in order to have more predictable mechanical properties. So thank you for your attention.